Hello everyone, thanks for joining our workshop. Today we are happy to introduce you to one of our newest hardware creation, which we call it the Generic Node Sensor Edition. This is the main PCB, this is how it looks like, and here's how the final device inside the enclosure looks like. In this getting started session, I'm going to give a brief introduction to the hardware, and my colleague Ahmed will present the software setup of our device. So without further ado, let's head to the bench and take a look at the device's hardware features in more detail. Alright. As you can see, the main PCB is very small and it only measures 61 by 33 millimeters or 2.4 by 1.3 inches. Here we have a JST-PH connector as the main power input. Having this popular connector and quite a wide voltage range from 2.3 to 5.5 volts, it allows us to use any type of battery which the voltage falls within this range. By default, we are using two AA batteries, which comes in a part of the enclosure as a battery holder and provides us 3 volts, but we can also use any type of lithium-based batteries like lithium-ion and lithium polymer to power it. Now let's look at some of the main components on the PCB, starting with the main power regulator, which is the state-of-the-art buck-boost converter with wide input range and only 300 nanoamp quiescent current, and it can deliver up to 300 milliamps. Next up is the brains of the system, which is the STM32WL SoC, and it's a dual-core version with Cortex M4 and M0 Plus running at 48 MHz. We also have a buzzer, 2 dedicated load switches for sensors and the external flash, tiny reset button, and the boot select jumper on the top right corner. The boot select jumper allows you to flash the device over UART. On both sides we have a standard pin header. The left one is used for programming and debugging the device, and the right one is to add external sensors and power to the device. We also have a quick and external antenna UFL connector to the device, so in case if somebody wants to add some more sensors or an external antenna to it. Now let's turn the device around and see what's in the backside. But the backside holds most of the sensors and the peripherals. Here we have a RGB LED and a user button, both of which are user programmable. We also have a flash memory, ultra low power and high performance accelerometer, a secure element, and a highly accurate temperature and humidity sensor. One thing worth to mention is that the temperature and humidity sensor sits right under the top cover, and there's a small hole to allow more accurate ambient temperature and humidity readings. However, to keep the device watertight and proper IP65 rated, as you can see, currently we don't use anything, but later on in the process we are going to use a water repellent mesh sticker, similar to the ones that are used in the smartphone speakers, to basically allow air to go in. As you can see, the button and the LED is also visible on the top side and has a very pleasant clicking sound. As we mentioned earlier, lower side of the enclosure acts as a battery holder, and 2 AA batteries which are installed in the same direction goes into this. And the middle section of the PCB holds a big battery clip, which provides a very good shock and vibrational resistance. As you can see, even if you drop the device, the batteries will be firmly kept inside. Now that we have a basic understanding of the whole device, we can assemble its components starting with the rubber gasket. This gasket provides weather protection against water ingress and jets. We also plug in the battery connector and gently tuck away its excess cable. And voila, the generic node is ready for installation. Now all we have to do is put the screws on and mount the device somewhere. But before we do that, I just want to quickly mention some things. If a user wants to add an external I2C sensor, and we also got you covered. On the right hand side, the pin header breaks out some I2C communication lines, and also there's a convenient little connector which is called quick connector, and the stemma and quick enabled sensors can also be attached to it. All in all, this first edition of the generic node aims to ease programming and deployment of the ready-to-use LoRaWAN sensor node at an affordable price, with full documentation and availability of the source files. Speaking of the source files, let's look at the schematics and PCB files, also go through some of the design decisions I made. Right, so here we have our genericnode.com website, which is the main information website for the generic node family. And here you can access the forum, the documentation. Right now, the documentation is not filled up, but we will soon add all the necessary information regarding the hardware, software, and how to easily get started. We also have a generic node repo in our GitHub, which hopefully by the time you watch this video, it will be available, and where you can find all the necessary hardware, design files, fabrication files, schematics, PCB, and the software SDK. There's also a nice little pinout diagram for it, and some short specs, a nice stack up, and the tools you used. Since the beginning, our idea was to open the design, and therefore we went with the open source tools. And basically, you can easily use a KiCad version 5 and to open the design file. Basically, all these files are in the hardware folder, battery holder, and here's the main PCB. And here are the schematic files. We'll quickly dive into the schematic files now, and then come back to the PCB analysis. Right, so here we have our main schematic file. On the first page, you can see we have divided the schematic into 3 different logical sections, namely the power supply, the LoRa microcontroller, and the peripherals and sensors. And we will look at each of these sheets one by one. Let's start with the power supply. In the power supply, here we have a main JST connector, and which goes through the ESD protection and the reverse polarity protection and the short circuit protection. And here we have some bulk capacitance to account for batteries with high internal resistance. And then the battery voltage goes to the buck-boost converter, and the enable pin of the buck-boost converter is being monitored by this voltage supervisor. This voltage supervisor ensures that when the battery voltage is too low, the battery should this is specifically to 2 AA batteries in series. And if the battery voltage falls below 2.3 to 5 volts, this will disable the buck-boost converter, and it will ensure that is stable and it won't go into the unstable mode. The buck-boost converter, as I also mentioned earlier, has a really low quiescent current of only 300 nanoamps, and it can deliver up to 300 milliamp output power. It has this is a RP605X, 2.8 volts output version. There are different versions, basically depending on your need, you can choose one. We have selected 2.8 volts operating voltage to save the power and also to ensure that the microcontroller will be able to provide full 22 dBm output power from the radio. The buck-boost converter also has a battery monitoring built in, which ensures that you can read the battery voltage and by enabling and disabling it, and it divides the battery voltage by 3, and it only requires 100 nanoamp of supply current. So this is very low power, and it has a built-in voltage divider and transistor switch circuitry and the voltage follower circuit. So now we have a 2.8 volts, and the rest of the system can be supplied with it. We also have a complementary load switches here, one for the sensors and one for the flash, external flash. This basically ensures that if you are not going to use those sensors, you can completely cut the power to it and save quite a bit of energy from the battery. Yeah, that's basically it. Let's go to the microcontroller section. We have picked, for ease of use, and also if somebody wants to change the design, adapt the design, and they can manually solder, a QFN version of the STM32WL. Although we've picked the QFN, this is the dual core and with the largest available flash and RAM sizes. And we have also went with dual output power version, meaning this can output both 22 dBm and 14 dBm outputs by just changing the switch position on the GPIO pins. This is a software configurable switch, and the antenna we've picked, it's very capable antenna, and it can emit radio in both 868 and 915 megahertz. So meaning by using just one single bomb, we can have the device to be used in both EU and US regions, probably in Australia and Japan too. And as a main clock source, we have a TTXO to provide highly accurate clock, and this is also power gated. And yeah, that's basically it. And yeah, there's also a matching network right after the RF switch. And yeah, these values later will be changed slightly to fully achieve the highest antenna efficiency. Right, and the last sheet is the peripherals and the sensors. Here we have external flash, which is 16 megabits, and we also have an accelerometer, which is high performance, really low power LIS to the H12 from ST, and we also have a SHTC3 temperature humidity sensor from Sensirion. There's a new version of this sensor. It's called SHT4X, and probably with the next revision we might use that one, because that one has even higher resolution for both temperature and humidity. We also have a secure element, the AT-ECC6088 TNG LoRa, and a buzzer circuitry, and the RGB LED and the user button. So both of which, so the user button and the buzzer GPIO pins, can be cut away, and these GPIOs are also routed to the pin headers on the right side. So if you're not going to use the buzzer or the user button, then you can use those pins for some other purposes. It's a very simple design, so that's basically it about the schematics, and let's go also quickly have a look at the PCB file. So here we are on the KiCad's main project window, and let's open the PCB layout editor and quickly take a look at the PCB. Here there are some layer stack-up information, and this is our main PCB. Here are the dimensions for it. It's a standard 4-layer PCB with 6 mil tracks and 6 mil clearance, and with a 0.3 millimeter via drill diameter. So you can go through one of the cheap fabrication processes to get it fabricated in China. So the first layer, it's mostly RF, some of the signal lines. Second layer also contains some ground plane, some low frequency signal lines. And the third layer is a power plane surrounded by the ground plane. And the last one, let me increase the contrast, and the last one is the ground plane, again to provide good RF and return current path. Yeah, that's basically it, and let's go to the 3D view. So yeah, this is how the 3D view looks like. It's very similar, it's extremely similar to the real world PCB. So 3D view inside the KiCad is really powerful tool, and I highly recommend using it. Alright, that's basically it from my side, and now I'm going to hand over the session to my colleague. He will walk you through the source code, setting up the tool chain, and how to flash your first code to the node. Thank you for tuning in, and see you soon. Bye.
I'm Ahmed from the Things Industries. I'm excited about providing you with a workshop on how to get started with the generic node sensor edition, and specifically the software. So we're gonna focus now on the GitHub repository. I'm gonna walk you through what's available with regards to the source code. We're gonna discuss the tools that are available and how to use them for building your generic node applications. I'm going to discuss flashing and debugging these applications, and we're going to discuss how we can develop LoRaWAN applications in general, and we're going to build our first custom application. Okay? Yeah, so let's jump right ahead. So if I jump to my browser here and open the genericnode.com website, you will find a lot of relevant information. Mainly the documentation portal is important, where you will find a lot of detailed documentation. So for example, if I want to find detailed documentation getting started, the sensor edition setup for the software, and we ask you to actually take a look at the generic node GitHub repository. So if I jump there, I will find a very simple structure of hardware and software. Hardware folder will typically have hardware related files such as schematics, PCB layouts. So if we focus now on the software side of things, we will find three folders: app, lib, and target. So target is typically files related to the target MCU or SoC that is on the board. And for now, we are using the STM32WL chip. So we will find the hardware abstraction layer for that SoC, and we will find a lot of other relevant target files such as the linker script and the startup and the configurations for the HAL. If I navigate back to lib, I will find sensor peripherals, drivers, and libraries that allow the application to actually drive these sensors and peripherals. So, for example, we will find the generic node sensor edition port support package, which is a very important library. We will find the stuff related to the onboard sensors, such as the temperature and humidity sensor and secure element. So if I jump back to application, this is where everything comes together. So in the basic app, for example, it's a boilerplate application that tests all the onboard sensors and peripherals and ensures that everything is functional. This is useful, for example, in production, where you are able to make sure that your device is functional before you actually start shipping it. We have also other applications such as the basic bootloader, basic FreeRTOS, and basic LoRaWAN, which we will discuss later. Alright, so that's a good initial start. So now, how about we start actually getting that repo and start developing for it. So if we want to actually get started with that repository, we should be able to clone it, and we would typically need git. So I open the terminal right now, and what I want to do is quickly copy the link of that repository and navigate to where I want to put that repository. So basically, I want to clone it or download it. And so, for example, for me, would be I'm gonna go to desktop, PC, and I wanna check out the develop branch. And I wanna tell it that all the libraries should be populated, meaning that if we have library dependency on other GitHub repositories, make sure that all of these are populated as well. So something went wrong. I don't know what it is. Okay, so yeah, had add an extra dash there. So it's downloading already. So you can see it already also populated the submodules such as the FreeRTOS kernel and the crypto authentication library from Microchip. So now that is ready, let's actually see how it looks like. So you will find the generic node sensor edition here, and the folder is similar to how we navigated on the GitHub website. So right now, it's a good idea to see how to start with that folder and basically jumping into the available tools. So we have a lot of tools that can be used and a lot of flexibility. So the straightforward tool is the STM32Cube IDE. This is an integrated development environment that is based on Eclipse, and you can easily download it. You will find all the links in the documentation portal. But if I open that application right now, I can press File and then import existing project into Workspace. It's already so if I it already sees the projects, but let's navigate again to showcase that. So if I press the things conference and then find the generic node repo and then go to software and go to app and then press open, I will find all the available applications. So if I press finish, make sure that everything's checkmarked, you will find all the applications that are available in the repo, and you can actually build them here. So I would, for example, click build project, and it will try building that project. As you can see here. Okay, so while it's building the project, let's see what are the other tools that are relevant. So for example, STM32Cube Programmer is also a very important tool and very useful tool. So this allows us to flash using the debugger and UART, and this is very useful in case you use any of the tools, whether it's the Cube IDE or any other tool like the command line or VS Code. So while it's building in the background, let's actually get familiar with how you're gonna flash and debug. So this is right now is the ST-Link debugger. It's an off-the-shelf debugger that allows you to basically flash any application to ST products. So this is the generic node, and now it's inside the enclosure. So if I unback it right now, like this, you can see what's actually inside. So these are the AA batteries, and this is the connector that is connecting it to the board. And so this is providing the needed power. And you will find here some pin headers and some other pin headers on this side. And these are already covered on the hardware getting started. But the most important part is this connection and these pin headers allow you to flash using the SWD protocol. So if I actually use that connector, for example, which is connected to the debugger, and I put it here so that we are actually uh, connected between the debugger and the generic node, I should be able to actually flash now the generic node using the debugger. And that is actually very important because now this is a production device that you can easily change the application of in production using just a very simple interface. So yeah, and it's also important to highlight that we have two UART pins, RX and TX, that are also connected here, so you can see what's happening on the device and if it's printing some useful debugging information, which is useful for our demonstration. Okay, let's jump back and see if the application already compiled. So we see here that it already compiled. Let me show you. So if I click here, so you can see it already finished and the basic binary is already generated. So this means that we can flash this application in multiple ways. So the first one is to just run it from here, and this will actually see what is the connected debugger, and you can see that it's trying to download it into the device, and then after it finishes, it downloaded and shows you successful download. uh, Another method is to actually use the programmer from ST, and we can connect with the ST link, and we can open a file. And in our case, we will find the binary in the directory that we of the application. So, for example, we used basic, so we should find it inside debug and then basic.bin, and we can also flash it from here. So after we opened it, we can press download, and you can see it downloading the application. Okay, so this is also another way of downloading the application. I think this is the most basic way and the most straightforward way of doing this. So how about we actually see if the debugging functionality is working as well. So we can easily say, okay, we're gonna put a breakpoint here. So and also open a serial terminal. Let me disconnect from this and open. So if I open a serial port to the right here, and we have the STM32Cube IDE here, we can actually click debug, and we can debug the basic application. So what is actually happening now is it's switching the workspace, and it's running on the device. So if I clear all the serial information and jump to uh, the breaking point, then let's just jump one step ahead. So we see that it's starting the basic generic node uh, sensor edition application. And if I keep jumping, taking a step after step, it's gonna report the battery level, which is part of the basic application. It's gonna start to test the LEDs and do more verification. So that is the basic app, and now we actually flashed it and debugged it using these ST tools. These are very helpful and straightforward to use. Once you set them up, you should be able to easily develop for the generic node sensor edition. So the other tools that can be used for development, there's a lot of flexibility when it comes to the generic node sensor addition repository. So if I shut down the Eclipse IDE, um, and the Cube Programmer, these are the ST tools. So there's other tools that are available, and we might not have a lot of time to discuss all of them, but you can use a Docker file to basically mount the generic node sensor edition repo and bind it and then build from there, so you don't have to set up all the tools yourself. There is also building from the command line, and there is also using Visual Studio Code. So let me show you how to use it from the Visual Studio Code, for example, because I know a lot of people are interested in that. So yeah, so if I open Visual Studio Code, and then open, file open, and then I can navigate to the things conference, and then I find the generic node sensor edition. So yeah, as you can see here on the, let me make it a bit bigger. So as you can see here on the left side, we have the same structure that we're familiar with right now. So this is useful in navigating to anything that you want to develop. So for example, we can see the basic app again. And how about flashing it and debugging using it? So that is also an interesting part when it comes to VS Code. There's a lot of flexibility, so you can actually use VS Code with Docker, and you can use VS Code with the command line, for example, and typing the commands to build, for example. But since this is all documented, I think we can skip some steps. So how about seeing if we can actually do some debugging using VS Code, which I think is most really important. And so for example, if I want to run and debug, I say that I want to debug in C, C++. This is gonna launch, and it's gonna give us options. So we're gonna tell it we want default configuration, but actually what we want is we want specific configurations over this. So I already prepared the configurations for that workshop to be able to use OpenOCD with VS Code. So I think it's this is all also available in the documentation page. But basically, if I open this launch.json and copy all the internals into our launch JSON within the folder. So this is also CBP debug, and it's also debugging the STM32WL, and it's telling it that we're going to use the basic LoRaWAN application, for example. So now let's actually build the basic LoRaWAN application so that we can actually debug it. So first of all, we're going to use a terminal. So if you can see what I'm doing here. So right now I want to navigate to software, and then I want to make a directory. And then navigate to that build directory, and then do a cmake command. So what is inside that cmake command? Let me actually make it this more. So what's inside the cmake command? It tells it to generate the build files for Ninja. I hope you can see it, so let me point it out. So it tells it that we're going to generate it for Ninja, which is one of the tools, and then we're going to tell it that it's a debug configuration, and we're going to tell it that we're going to use the crust.cmake file, and we're going to build the application that is called basic LoRaWAN. So typically when you do that, it's gonna invoke the cross.cmake, and this needs to be set up first. And before running that command, let's navigate to cross.cmake, and we will find that there is an important header that tells you that you need to set up the prefix of where is your compiler, basically. So for me, I'm using now Mac, so I find this nice comment, and basically I set up here so that I'm telling it that my compiler is gonna be in users Ahmed Elsalahy, and then it can be anywhere for depending on your file system. Okay, and you can also, of course, do that for Docker as well, depending on your which tool that you prefer. Okay, so right now let's quickly compile. So jumping back to the terminal, and we already have the command ready. So I'm gonna press enter. So this command, as you can see now, generate all the files for Ninja to be able to compile the project. And once we do that, we can actually type Ninja -v, and basically this tells it, okay, we're gonna compile the basic LoRaWAN application, and this is running all the compilation commands for each file that is related to, for example, the libraries or the LoRaWAN stack, and it's combining all of it and putting it into one application. So we're gonna wait for that to compile. Okay, so now that we compiled the application, we wanna run the debugging launcher. But one thing that we want to make sure of is that we set up the application in order to use the debugger. And one of these things is by going to the basic LoRaWAN application, and with each application there's going to be a configuration folder, and this configuration folder allows you to actually tell it what you want to do. So for example, application conf.h allows you to say, okay, I want application logging, I want the debugger to be on. So for me, I will do this by one, and then I want to tell it to disable the low power, because we want to run it in debugging mode, so it doesn't really matter. So if I actually save these configurations, I need to actually combine one more time so that we are able to see the debugger running through the application. And now I go to the debugger and run. So this is going to use our launcher that we added, and it's going to try to halt the system at the point where we added the breakpoint. So you can see here it already goes to head init. If I step over and jump into the LoRaWAN init, there is a system app init. So there I can go and see that we're initializing something related to the clock and the RTC. We're doing something with timers, and we're initializing the IOs, and we're initializing the debug pins, and then we're initializing the terminal so that we are able to see some logging. And then you can see that we have a comment here that tells you, okay, let's init anything related to the board. So this application is really low power, and so it's a very good boilerplate. So what we want to do is, for example, initialize the LEDs. So this application doesn't have any LEDs in it. So a good way to do that is basically jumping to the basic application and seeing how we do that there. It's really simple. We find that there's an application function called LED toggle. If we actually jump to that function, we find that, okay, it's easy. Let's init the LED blue and the green, for example. So let's init these LEDs and print something like this. and then turn them off. So we're gonna copy this back to the LoRaWAN application that we were in just right now, and yeah. So this is actually a copy and paste to show you that, okay, we're gonna just initialize the LEDs, but we have no idea what's the delay, so we're gonna actually make it 100 milliseconds. Okay, so this actually is a good way to configure the basic LoRaWAN application using another boilerplate application. So we wanna toggle the LEDs 3 times before before actually doing some low power management initialization and doing the LoRaWAN application initialization. So let's compile this again. So now that it compiled the application, we want to see if it will actually come here and actually try to init the LED. So let's put up another breaking point, and we need to also have a look at what's happening on the board. So let's bring that here and put it to the side. So yeah, so what's happening here is basically running the debugger in parallel to the node, and let's see what's gonna happen. So I'm gonna also flip the device to the other side so you are able to see the LEDs being toggled. So yeah, so if I navigate to this, you can see that I'm initializing the LEDs here, but then if I run, it's gonna blink 3 times and go ahead with the application. Okay, so that is it. For now, it's a good idea to wrap up. Basically, what we discussed in the session is all the topics that we agreed on. One final tip is how LoRaWAN applications are typically developed. If I open an image here, this is a model of a typical LoRaWAN application. The node typically sleeps most of the time. It wakes up, it measures and reads the data from the sensors, and then processes that data, and then wakes up the transceiver if it's the good time to transmit something, and according to the duty cycle and all the regulations. And then it transmits that data and then receives some data using the RX windows and then goes back to sleep. This is a typical model. You can typically customize your application based on that. A basic LoRaWAN application, for example, provides you with all the capability to do something like this easily, and you just need to add the sensor or your custom application, and you're able to start with the production of the device with that specific application. Okay, so I think that is it. Thanks a lot. I hope that this was informative, and looking forward to seeing you in a deeper dive into the generic node firmware features.